Hi everyone, I'm Vandana, and we are going to start today on overcoming DDR routing challenges with advanced PCB design and DFM practices. So let's just start with Sierra Circuits. Sierra Circuits is a one-stop solution for PCB fabrication, assembly, and component management services, of course. We have a 70,000 square feet PCB manufacturing and assembly campus in Sunnyvale, California. We offer advanced technologies like HDI, rigid flex PCBs, RF, and microwave PCBs.
Vandana, I think you forgot to switch the slide.
Yeah. Yeah.
Okay, you're good.
So yeah. So this is the agenda for today. We're going to deal with each one of these one by one, and we start with the 6 benefits of DFM that we have listed down here. By following the DFM rules, you can ensure the manufacturability of your design. When you design a product with manufacturing in mind, you can identify and rectify potential defects early in the process. So DFM minimizes these chances of expensive rework during production. DFM optimized designs are easier and quicker to manufacture, hence leads to shorter production cycles and faster time to market of the final product. Uh, we'll discuss typical DFM best practices now to avoid manufacturing delays and ensure reliability. The first one that you have to do is choose the right material. Uh, if you want to avoid overheating and mechanical damage, you can follow some of these DFM rules while selecting PCB materials. Uh, you can select materials with dielectric constants and dissipation factor that are less than 4 and 0.005. And this will minimize the insertion losses. You can ensure your selected material's glass transition temperature is greater than 170 degrees Celsius. And the CT along the Z-axis should be less than 70 ppm per degree Celsius. The thermal conductivity should be higher than 0.5 watts per meter Kelvin. Another point to keep in mind is to ensure uniform material thickness within specified tolerances and use low moisture absorption materials such as the polyamide or PTFE to prevent delamination and long-term reliability issues. Next is to design a reliable Stackup design. You can ensure symmetry in your PCB Stackup to avoid bow and twist and maintain even stress distribution. And unbalanced Stackup usually causes board warpage. You can route your DDR signals near the ground planes to minimize the noise. Have dedicated reference planes adjacent to high-speed signal layers, and this will avoid crosstalk. Uh, you can also collaborate very closely with your PCB manufacturer to fix the tolerances, typically within plus to minus 10% of the target thickness. The combined dielectric and the copper layers often do not align with the final board thickness after the plating and surface finishing. You can also consider copper plating, solder mask, and surface finish layers before finalizing the board thickness. Next is to maintain optimum trace width and spacing. When it comes to trace routing, inadequate trace to board edge spacing might expose the outer conductor to external corrosion. Incorrect conductor spacing might also result in inaccurate etching and short circuits. So we have listed a few key design practices over here to prevent these issues. First is you can ensure you can ensure clearance of at least 15 mil between copper features and the V-score line, and maintain a minimum board to edge spacing of 7 mil for inner traces and 10 mil for outer traces. To minimize crosstalk, keep your DDR signals away from other high-speed clock lines and power tracks. You can follow your CM's minimum and maximum line width and spacing requirement based on the copper weight. At Sierra Circuits, we can achieve a minimum trace width and spacing of 1.5 mil. So we have some standard VR design clearances listed out here to avoid electrical shorts, crosstalk, solder bridges, and reliability issues. And you can implement these 4 VR design clearances. The first one being is the minimum clearance between via and routed or scored edges is 10 mil. You can incorporate at least 8 mil of drill to copper clearance. The antipad should be 16 mil bigger than the hole size, and the plane relief should be 8 mil. The clearance from the solder mask should be 2.5 mil larger than the pad diameter. Uh, Next, we have setting the accurate annular ring and drill dimensions here. So when you're designing annular rings, ensure your requirements align with your manufacturer's capabilities. Otherwise, issues like tangency and breakouts might hamper the design reliability. You can follow these recommended annular ring sizes to avoid these issues. That is 2 mil for laser drill vias, 3 mil for mechanically drill vias, and 5 mil for component holes. Missing copper pads for plated holes can lead to connectivity issues. So verify that the plated holes have copper pads on all the layers. Inadequate drill to copper clearance might increase the risk of short circuits. So to prevent that, ensure minimum clearance of 8 mil. A large aspect ratio might create via plating issues. So keep the aspect ratio at about 10:1 for through-hole vias and 0.75:1 for microvias for optimal plating. Here, there are standard drill and pad diameters for half-ounce copper PCBs that we have presented here, following the IPC Class 2 and the IPC Class 3 standards. The left table outlines IPC Class 2 specifications that are commonly used for standard reliability applications. And the table on this side, the right side, outlines or presents IPC Class 3 specifications, which have stricter requirements for high reliability aerospace and medical devices. Here you can see the standard drill and pad diameters for various copper thicknesses based on IPC Class 2 and IPC Class 3 standards. These guidelines help ensure accurate hole and pad sizing based on copper thicknesses and layer count for manufacturability. To ensure correct trace termination and minimizing the impedance mismatches, we need to employ series resistors near the source and the parallel termination at the receiver. So keep these traces between the resistor and the IC as short as possible, and avoid using vias in the termination path as they introduce impedance discontinuities. Choose resistor packages that are suitable for operating frequency and PCB layout constraints, and smaller packages are obviously preferred for high-speed designs. Ensure resistor pads have proper solder mask clearance and pad spacing to avoid solder bridging. So we have presented a case study here on termination routing in multiple DDRs connected to an FPGA. In this design, we have 4 DDR3s that are connected to the memory controller, which is an FPGA. The configuration uses a flyby topology in which each DDR chip is connected to the FPGA memory controller in a daisy chain fashion. The DDR datasheet specifies a nominal termination resistor value of 36 ohms. But we have selected 35.7 ohms resistors here as the optimal choice for our designs. It was challenging to place termination resistors due to the large size of the components. And initially, termination resistors were positioned at each DDR ends using vias. Unfortunately, this approach resulted in undesired trace stubs causing signal reflections. Our designers then used the 0201 instead of the 0603 package to accommodate the termination resistors into the board. We implemented shunt pull-up termination resistors at the end of the last DDR to minimize the trace stops. To achieve accurate impedance control, we have to stick to these tips over here to avoid, impedance mismatch issues. Ensure your fabrication drawing and design files include all the controlled impedance traces. And avoid splits in the reference planes. Keep the consistent gap, preferably 3 Ws between differential pairs. Maintain uniform trace width and clearances to avoid impedance mismatches. and implement via stitching along ground planes. The recommended spacing, as mentioned, is lambda by 8 to lambda by 10 between the adjacent vias. Ensure copper poles are grounded correctly and incorporate a solid metal enclosure without gaps around the RF circuit. Use serpentine routing for length tuning, but avoid excessive bends. So now we have a small demo on the impedance calculator tool that we offer in our Sierra Circuit website. Our Sierra Circuit impedance calculator uses the 2D numerical solution of Maxwell's equations for PCB transmission lines, and it also renders fairly accurate results. This impedance calculator tool supports 82 impedance models with multiple geometries. As you can see, the uncoated, coated, and embedded microstrip here and the strip line. And each of these specific models, you can choose the single-ended differential pair, coplanar, and all of these options here. The tool is also integrated with the signal loss and the uh, signal loss S parameter and crosstalk calculator, which I will be showing to you in a moment. I've just opened some of these models over here to just show you how the calculator looks like. For demo purposes, let's go with the coated microstrip differential pair impedance calculator here. We start by entering the input parameters, uh, the dielectric height, a dielectric constant. Let's go with a coating height H1C of 1.5 mils. The coating height H2C and the coating dielectric constant over here, these already have a default value, but you can change it if you wish to do so. Let's go with the coating height H3C 1.5 and enter delta W here. Delta W is the difference between the top of the trace and the bottom of the trace. You can click on this help content and a table will be displayed that suggests delta W values based on the starting copper weight. You can use it as a reference. Let's go with 0.5 for now. Enter trace thickness, trace separation. To calculate the trace width, we have to enter a target differential impedance here. Let's go with 100 ohms and click on calculate W. If you want to calculate the impedance, then you have to enter the trace width instead and click on calculate ZD. So once the calculation is done, you can see that the coupling coefficient, propagation constant, and all of these are calculated and displayed here. Then we have the signal loss calculator for the same chosen model. You just have to enter the dissipation factor, the frequency. Let's go with 6 as a surface roughness, which is a standard roughness for a foil, and enter a length of 2 inches. Click on calculate loss. And the signal loss output in the odd and even mode are calculated and displayed here. Next, we have the S parameter calculators. We enter the source impedance, a load impedance. Choose this drop down here to choose the output type and click on calculator S parameters. Since this is a 4-port network, we can see that the 4-port S parameter and mixed mode S parameter matrices are displayed here along with the characteristic impedance and the propagation constant. One thing you have to make sure before using the S parameter calculator is that you have to use a signal loss calculator, because the frequency that we have entered in the signal loss calculator is used in the calculations here. You can of course go back to the signal loss calculator and change the frequencies if you do wish to calculate these outputs at different frequencies. Then we have the crosstalk calculator here. The geometry is shown. We'll enter the couple trace length. Let's go with 200 picoseconds for the signal rise time. Enter signal voltage and click on calculate crosstalk. The near end crosstalk and the far end crosstalk calculations are displayed here. I'll just go back to the slide now. So now we start with the placement of decoupling capacitors to reduce noise. Here you can choose capacitor package size as mentioned 0402, 0603 or 0805, any of these that fits your board space and manufacturing needs. Ensure that the capacitor can handle your circuit's operating temperature range though. Use multiple capacitors to cover a broad frequency spectrum and ensure effective decoupling. Always check the capacitor data sheet for detailed specifications and the tolerance values. When the power planes are spaced apart, the loop inductance can significantly affect circuit performance. To mitigate this, we place the capacitors close to the IC's power and ground pins. You can avoid using long traces between the capacitor and IC power pin and align the capacitors in the same direction for efficient PCB assembly. To shorten the distance between power pins and capacitors, place the decoupling capacitors directly under the BGA on the reverse side. Do not place these capacitors over large vias or on BGA solder joints. Now we have some common solder mask defects, such as missing solder mask or excessive mask clearance that might expose traces, incomplete or missing mask openings, solder mask sliver, And to avoid these issues, we have to maintain a minimum solder mask web of 4 mil for green and red solder masks and 5 mil for the other colors. Set a solder mask clearance 2 mil larger than copper pads with a 1 mil annular ring. Uh, Also, keep a 1:1 ratio between mask openings and copper pads. Define a solder mask relief areas to avoid interference with component placements. You can incorporate these mentioned DFM rules here when you're designing a silk screen to make sure that the silk screen is legible. You can have a minimum 4 mil line width and 25 mil text height or width to ensure legibility. Specify the logo size and details in your fabrication notes and avoid overlapping reference designators to ensure legibility. Do not include silk screen over vias and under the components. It can block access to solder points and hide the markings. And always use the standard color that is white to maintain the consistency. As marked over here in the image. We have a 6-step process here that we follow at Sierra Circuits for DFM validation. We start with our DFM engineers who review the netlist for short or open circuits, annular ring sizes, clearances between copper features and word edges, solder mask, and silk screen dimensions. We then provide clear recommendation on how to modify the design to resolve the detected DFM errors. Once all these errors are resolved, the project then moves on to production. So we have cited a few blogs and design guides over here that you will that are available in our website and are relevant to DFM and DDR memories over here and checklist, of course. This is Amit Bail, our Chief Revenue Officer, and his contact details are given here. We also have a PCB forum Sierra Connect network where you can ask whatever questions you have, and our experts will get back to you soon and answer those questions for you. We have also mentioned some of our PCB manufacturing capabilities and some of our PCB design services that we offer here at Sierra Circuits. You can connect with us for a design quote then. I'm going to stop sharing now. Thank you for your patience.
Thank you so much, Vandana. That was great. Orlan is going to take over now.
Come off of mute.
Yeah, we can hear you now.
All right, thank you. What we're going to talk about is the DDR. I only have 2 slides. Those slides can be made available to you. Basic understanding of what DDR3, DDR4, and DDR5 design techniques are. Cost is what I find driving most customers. DDR3, of course, being the cheaper of the DDR5. The thing I like about the DDR5, it's more forgiving because it has the on-die arrow correcting code. So I don't have to be just as precise with my routing it will make up the difference for me in there. But again, this is available for you. So let's talk about Stackup. Stackup's very important part of the process in what you're doing. And what I love about our software is I can come in here and I'm going to be concerned about my Stackup. And I'll go ahead and open this up. And of course, it popped in the wrong screen. Let me drag that over here. So here's my Stackup that I have. And the important thing I want to stress is dielectric core, meaning that your fabricator's buying this as a panel, the top and layer 2, however you understand that. So that's their core that they're purchasing. You can't change that dielectric between there. The only dielectric you're going to be able to change is between the two panels that they will press together on there. What's important about this is the fact that to make sure that the material you're using, they have available in stock. Make sure your values are correct as far as the Stackup is concerned in there. The software will give you the overall. So if you create this on your own, like I have, then I want to export it out and I want to send it out to my board house to say, can you build what I want to create here? Give me the pitfalls, the materials that I might be using that I need. So I might have different material needs, the Rogers material, the FR4 in here. So I get back that information and I can import in an IPC 2581 from the fabricator. Let me drag that over. My apologies. I tested that. This was actually sent to me for this demo. So I'll go ahead and just load that in. And of course, it's warning me that, there's no going back. And my screen is not cooperating. So I'm here looking at my different materials that is used. It's given me a summary of what has changed. So I can go ahead and click on here. And basically, I already had my silkscreen top and my paste mask top and my type of finish I wanted for my top already in my Stackup. I didn't get that from the fabricator. I could stress that, but that isn't necessary. What's important is the Stackup. What is the core material? What has changed? What's got renamed in there? So the plane possibly got renamed and what got deleted. And that's what I'm concerned about. Again, they've done the work, so I'll just go ahead and accept what they've got. Now I have a new Stackup, and I can go into my Stackup here. Let's expand that out. And I can see that the material has changed from what I had. They're using the FR 370HR material where I had a Rogers material in there. And notice that their cores are different too. Their cores were the two planes as a core, where mine wasn't. So the core had actually changed from what I had first depicted, and pre-preg materials now on the outer. So it's very important that you communicate this with your fabricator to make sure you guys are on the same page. They can build what you want built, and they're your best advocate really to go to for the materials you need. And again, I can't change that core. That's a panel they're buying. So that's important to know that and utilize that during that time on there. So I'll go ahead and say, okay, that is part of the Stackup. Let's talk about Constraint Manager now on there. And in the Constraint Manager, basically it's where we're putting our rules in. And I can go in there and I can put all my electrical rules in there, my physical rules in there, and my spacing rules in. Same net spacing also. We'll talk about manufacturing later. In my routing there, I have my relative propagation delay. With DDR, the reason we call it relative propagation delay, because my clock signals, my control, my address, my byte lines are all relative to each other. I need them there. The timing is important to be there. I can come up here and I can go ahead and do analyze, a little slow, analyze in here and see what my values are, and then come in here and find out where I'm not reaching the requirements I need. I'm expecting a delta of 0. Of course, perfect, can't get there. And my tolerance is 5%. In some cases, I have 100%. I'm running from all drivers to receivers on there. I can expand this down and actually see where I'm coming up short. It will be between these two pin sets. Now, you see pin delay here. The higher the speeds, of course, then we consider all copper to be important. And that pin delay is actually that wire that's between the die pack in the chip and the pin that gets soldered to your board. That's real copper. We account for that. You get that information from the vendor, and you can put that in there because what we're wanting to account for is true copper length, and that is still some copper length that we need to adjust for. So that's what our pin delays are. Of course, pin 1, the driver, pin 2, the receiver on there. And again, your fabricator will give you that information on there. The other thing that our software will do is go ahead and calculate the z-axis of your via. That's real copper, that's real length. So that should be part of your calculation to hit your target length that you're needing in there. So that's important too, to go ahead and know how thick the board is and know that how many vias you've got in there, and that's true copper length that you're going across there. So next, let's go ahead and talk about placement. And I went ahead and preset this up so that we can go ahead and talk about placement without taking a lot of time on there. So I have my DIMM memory. So you might be designing your DDR where you're using a memory stick, and here's my connector for that. The byte lane should be quite the distance. What I do is put them on alternating layers so that I've got the separation I need on there. But again, that tuning is important across there. Now let's go ahead and talk about on-board design. So I have some on-board memory. Here's my processor and my memory chips. Here's the first group, and here's my second group here. So we've got a routing process that we're going around into, kind of like a I2C type routing as we go ahead and route these in there. Again, placement is important. This type of memory chip, it's kind of hard to put them back to back, meaning a front and back side assembly because of them stacking right on top of each other on there. Let's go ahead and then talk about our termination on there. It's important, as you can see on the far left here, I've got my capacitors, and I'm trying to get them as close to the pins as possible in there. And then outside at the very last chip that I have, there's my termination. Now, what I've done in the past, and I found it to be very beneficial, is to go ahead and route all these. I don't even place my termination resistors till at the very end, because what's important is from the driver to the receivers, of course, that flight time. And then at the end, I'm just terminating. I try to match those as close as possible, but they're not as critical because what is it doing? Just terminating the signal. But again, the placement of those is important, and I'll just go ahead and wrap that placement around the chip and then fan those out for my termination on there. So that's very important to keep in mind. The other thing I want to point out is the tuning. So you really need to tune these nets, and again, you can see how much tuning has been done in here. But what I like about the software is once I've got these rules in the constraint manager, I'm just coming in here and I'm going to say auto tune, just grab all those nuts and just let the software do the calculations. The software go in there and do the tuning that I need. There's no point in me having to do all that work. The software knows the rules that I want. It's following those rules and it tunes that. Notice that during this selection, I still had my differential pair clocks here, and it didn't tune those because there was nothing to tune about it. It was already within the rules that I had set up for it. So that can save you quite a few weeks really on a board like this to be able to go in there and actually do the auto tuning in there. Now, the other thing I want to go ahead and talk about, and that was the other slide here that I want to show you. Again, I had two slides, is during that placement. And again, this is available for you. That termination that I showed you with those resistors are very important, more important in the DDR3 than it is in the DDR5. But the placement is still very important on there. And again, this slide is available for you on there. Let's jump back to our board. And then at this point, I want to go into our constraint manager. Again, this time I'm going to jump down to manufacturing, which I told you we would talk about here. So let's go up here. And I have my DFF settings. Here are some board vendors out there. I've decided to remove all the values in there because that is something that they kind of hold close to their vest. It's their proprietary information. They will give that to you. You can insert that into our software, and then you are literally checking your design as you design it to their requirements. Now, I've been around a while. I can remember days where I'd send my board file off on a Friday, expediting. I wanted to work on it over the weekend, only to come in on a Monday morning to open my emails and find a laundry list of things I didn't follow. It was their rules, their minimum requirements. This is taking that away. This is when you're done with your design, you're really done with your design because you're putting their rules in there and you're checking your design to their rules. So here's my board houses. I can come down here and click onto my design. And at this point, oops, let me go back here. There's my design. I can come back here and I can decide who I'm going to check my design to. And then I'll select that board house that I want. And then I'm going to go in there and I'm going to check to their rules that I would have set up for those. Then also in Sierra Circuit's case, they're also a assembly house. So here's 4 or 5 different assembly houses that I've used in the past. They'll give you those rules. The last thing you want to do is design a raw card that no one can build. So go ahead and get those assembly rules right up front, how close you can have a package to package, depending on whether it's a double IR or a wave process that you're doing. That spacing requirements on there, spacing to the edge of the board, spacing the cutouts, those type of things that we've discussed with you. Paste mask, fiducials that's needed. Those are the type of checks that you're going to be doing in there, and you can go in there and check that, again, your design to those different requirements. The whole idea of this, and we also set that up also for our tests. So we have a few test fixture houses here that bed and nails type tester, flying probe type testing. All this information, what we're trying to give you is no longer is it a post-process, and you might have heard the word valor sometime in your career. Valor is a post-process. I'm done with my design, or I think I'm done with my design. Now I'm going out there and I have to run through this valor check only to come back and redo my design because I'm not matching it. That's why we're wanting to put it up front to the engineers. You've got this information. You know what the rules are. Follow the rules. When you're done with your design, you are truly done with your design. Your manufacturer can not only fab your raw card, but also build your assembly for you also. So that's really what we're wanting to do, is to bring that type of information up front, not making it a post-process and adding time to the design cycle that you would have in there. So at this point here, I will go ahead and pass this off to Jerry, who will talk about simulation for you.
All right, thanks, Orland. Let me go ahead and get my screen set up here. So I'm going to start with a slide, and basically this is just to kind of put things in perspective. See if I can just get rid of this here. So once you're done with layout and you got everything ready to go to fab the board and everything, one thing you probably want to do is check your signal integrity. With interfaces like DDR3, DDR4, it's a pretty, in some cases, it's a pretty fast interface. Others fast, some are faster than others. So you want to make sure those signals are actually the integrity of the signals, the signal shape and everything is actually getting to the receivers like you want. So that's where signal integrity and power integrity come in. What we have as an offering allows you to run pretty much the gamut of signal integrity and power integrity. If you look at this slide, from the left side of this slide, we have tools that will allow you to check signal integrities, kind of a screening test. directly from your layout tool. So as you're in Allegro or OrCAD Pro and you're designing things on, kind of on the fly, you want to check something, maybe you laid a few traces, you want to make sure your impedance maintained consistently. You can do that right there on the canvas with some of the tools that we offer. When you need to get away from that and get deeper into signal integrity, for instance, with DDR3, DDR4, you want to focus on that particular parallel interface. Then you want to come in and probably transition into the more specific tools, the more focused tools. And that's where you come out of the PCB environment and you get into the Sigrity environment. This is the basically the Sigrity tool set offers power integrity with our Celsius Advanced PTI suite. This covers both AC and DC, as well as a little bit of thermal. So you can get some I2R type of analysis, as well as IR drop, as well as decoupling capacitor optimizations and things like that. So that's kind of the power integrity side of it. Signal integrity, we have a main tool that allows both parallel bus and serial channel. And then we have three options for that, for this serial, or for the signal integrity flow in the time domain. We have three options for extraction. So typically you want to get the board parasitics accurately represented into a model. And we have three options for that depending on your signal speeds. So that's kind of where I'm going. I'm going to focus on signal integrity for this particular board that Orlin was talking about. So let me kind of move that, and I will first jump down to the board Orlin was working on. So this is kind of my starting point here. What I'm going to just kind of give you a layout of what the board looks like, what we're trying to simulate. And so this is the board that Orlin was working on. This is the onboard DDR interface. And so I'm starting at U34, which is our controller. And then I'm going to focus on just this bank over here. So we're going to go from here to this bank. You can see it's inclusive of the resistor terminations for the address network there on the last one in the chain, as well as some of the specific layers have the routing, and you kind of see how that routing ended up going there. So this is what I'm going to focus on setting up and basically doing a signal integrity check on it. Make sure my signal flows are good. So starting here, just to kind of give you a lay of the land of where I'm going. Now I'm going to move into how you get to what you need. How do you get the information off the board? How do you get that information into a simulator where you're running data patterns and verifying the quality of your signal interface? So this is the tool that we use to do that. It's called Topology Explorer Workbench. It allows you to set, it's basically a topology editor. It allows you to set up various blocks. We have templates you can start from that already have a complete path, and all you have to do is associate each block with the set of models that you're dealing with. Typically controller and memory are IBIS models for DDR3. So these are typically models you get from the vendor. And then you need to represent what your PCB looks like in between the controller and the memory devices. And so this is the extraction process I mentioned earlier. There's a couple of ways to do this in our tools. One is to just start from a layout block. So you can come over here to the individual elements, put a layout block down. You kind of point to the board file that it's going to basically extract, and you can see here it's just going to take you out to find a particular board that the board of interest, the board that you're working on, and then it will basically point to that particular board. And then in our case, it's just taking in a regular Allegro BRD file. We do support other flows. You can bring in ODB++ and IPC 2581 as well. But that's the starting point. You can put the layout block down, and then over here, you choose your extraction engine. And there's three to choose from. The very low level is a SPICE model. The next level up is a 2.5 dimensional solver that will generate an S parameter model of your board extraction. And then there's finally, if you're really pushing the envelope with signal speeds and things, Clarity is the 3D solver that we offer. So all of these are available for extraction. So you select your extraction engine, and then once you do that, you're basically ready to go and go into the extraction tool set. And this is the tool this is the PowerSI tool. That's kind of the mid-level extraction tool. Once this brings the board in, it brings it into the Sigrity environment. Then you kind of just work down the workflows here. So, the first step's done. It's if you've come from Top XP, it comes in as a loaded file already, ready to go. You can check your Stackup. Remember how important the Stackup is in this particular flow. You can make sure it translated over correctly. If there's any kind of setup changes, you can certainly do that. This is a full Stackup editor. If you need to make some, what if analysis, maybe thicken a layer or change a material, you can see immediately what its effect is going to be on this. You won't have to go do it in the editor and bring it, retranslate back in. So you can do it all from within this tool. Once your Stackup is ready, next is you're selecting your nets. So when you select your nets, what's going to happen is you'll get a net list over here. So the tool needs to know what nets that it needs to extract, what nets to focus on for the simulation. So you can come over here and basically select all the nets in the board that are of interest to this interface. And in this particular flow, I've got basically the VTT threshold because I want to include my terminations for my address bus. I want to include those terminating resistors in the extraction. So I'm turning on the VTT shape. I want to make sure I have a ground enabled. Got to have grounds for this. And then now I'm down here selecting all the elements of the interface. So you can see it's all the address buses, data buses, everything associated with this DDR3. Once those are enabled and selected, then you essentially the next step is to come down here and generate ports. Ports is connectivity for the board so that when you generate this model, you can connect IDIS models up to it. So if I go over here to generate ports, I've already done this, so I'm just going to come in here and just show you the port connectivity. What it's going to do is based on these nets that you have selected, it's going to put a port in there for these particular ports. And so here's the ones that I've enabled here for inclusion. Notice you can specify port termination, and typically it's 50 ohms for data, but sometimes it's 40 for address, or maybe you're doing 45 ohms for data. You can certainly change these to match whatever your impedance characteristics are going to be for your data and address bus. And then once you select these, then it's going to generate these ports and then put them in place for the simulation extraction. So I can go ahead and close that. One other thing I want to note is in the component manager of the tool, and this is just simply a manager that shows you all the components on the board, basically whether their condition, what it sees that's going to be contained in the design, and what they look like to the tool. In the component manager, I want to make sure that I have my termination resistors enabled. And in this case, you can see if I select any one of these termination resistors, they have a green check mark here, which means they're going to be inclusive in the extracted model. They're going to be within it. So all I have to do is apply a VTT power threshold to do an address bus situation, do an address bus simulation for the proper terminations. As you can see down here, there's a 39 ohm resistor in place for that. That's the model that it sees, is just a resistor, 39 ohm resistor that's going to be in the extraction. Once that's done, then you're ready. You start the simulation. Obviously, I'm not going to run it, but once it completes, it's going to give you an S parameter chart. You can look at the particular signals of interest. This is all the ports that you connected. It's looking at S parameter performance, things like return loss, insertion loss, everything from port to port. And you can do basic analysis here. If you're adept with S parameters, you can tell certain things. Maybe some things don't look quite right. You can do some quick analysis that way. But if you're satisfied with this, then the next step is, now you have this S parameter model. The next step is to map that to this block. And I'll go ahead and remove this. So the next step is bringing this into your topology. So again, I mentioned that you can start from a template. In this case, that's what I did, and I just duplicated some memories over here. So I've got an IVUS model for my controller. And so if you select that, double click over here, you see the IVUS selections here. And you can go out to the IVUS selector, walk out to the IVUS model in your system, the IVUS model you got from your vendor, select it in the list, and then set up the bus types you want to do, set up what the content of your data bus and address are going to be based on the IVUS model. And then essentially that's ready to go. So then that points to the particular IVUS model that you want to run for the controller. The PCB is what I just extracted. And so in that case, what you're doing is looking for the extracted file. This happens to be a S parameter model that I extracted. And typically when you extract with Sigrity tools, you'll get an S parameter model that has what we call a SPICE wrapper. So the SPICE wrapper helps with connectivity, makes connectivity really easy. And then it calls the S parameter for the performance. So you just map to that, and then your PCB block is updated. See all the ports, there's U34 for the controller, all the memory devices over here, and then finally the IVUS models for the memory. This is identical to the controller setup, so I won't go into much detail here. So this is how you get your topology put together. The next step is you want to go through and set up everything starting from, again, Sigrity is very good on this in terms of workflows. You want to start at the top of your particular workflow. This is the parallel bus analysis workflow, and begin to kind of walk through each one of these steps. So we've got the topology set up. So the next thing is to check connectivity. This gives you a rough estimate to basically show you whether or not your connectivity and what each receiver sees as a driver. This is what that's going to do. So it's just a quick sim there. Next is analysis options and timing budget. Timing budget's more of the constraint side of things, what you want to see performance of the board measured against. So you can use default settings, or you can use your own here for setup and hold and things like that, skew measurements. Once that's set, then you go to your analysis options. This is where you set things up like the data pattern you want to utilize. You can randomize this. You can use just regular alternating patterns. Very flexible here. You can also set up what driver models out of the IVUS files for the controller and memory. This is where you set that up. So if you have multiple drivers to select from, you can pull this down and make those selections. And so this is the controller selection, and right now it's set up for address. That's why the address buses are showing up. And then the memory, on the memory side, you see the same thing. You see the memory receiver IVUS model over here, and the drivers and the driver models available for that. You set your data rate up here at the top, and that typically gets automatically compensated for the necessary clock period, the clock signaling, the bit period, however many bits you want to simulate. And then to control whether or not you're doing write, read, address, you select this bus simulation tab and go into address, or select address, read, or write, depending on, or all three, depending on what you want to do. And then that's about it. Once you have this set up, then you're ready to basically save the topology and start the simulation. And I've already ran this, obviously, since I don't have a whole lot of time to deal with here. So this is what the data bus looks like. Just did a quick extraction, and probably have a little bit of reflection going on. Probably chose the wrong model driver or something on my IVUS model for that. But this is basically going to show you what it looks like. Once the simulation's done, depending on what you ran, you'll see a listing of the results over here. And in this case, I'm looking at memory device 1, what the signals look like at my very first memory device for data. You can do the same thing for address. I have address in here at the very bottom. So if I shut these signals off, I can come down to address and just take a look at what the address lines look like. And so if I take a look at that and then shut off the clock, I can see various address responses here. You can see that in just a regular time domain format. You can also switch over to an eye diagram. So you can easily look at what the eye diagram looks like. You can also put in specifics on the particular protocol you need. So if you're trying to meet a particular protocol, we have all the JEDEC standards for protocols for most of the standard interfaces For instance, if it's this one, you can kind of set that up and see the data mask coming in, see what it looks like for address requirements, things like that. So, very quick overview. That's kind of what I intended to do here. I'm pretty much at the end of this. So if there's any questions, I think we're about to open the floor for questions on any of this particular flow in addition to my simulation flows.
Oh, yes, thank you very much. Okay, so I'm going to ask you guys to answer a very quick poll. Actually, it's not quick. I think we have like 5 questions. But I'm going to leave the poll open, while we do the Q&A. And just one very quick thing that I would like to share with you before we start with the questions. I just want to say that I will send you an email with the slides and recording this afternoon, and I will give you a link to our upcoming events. And specifically, we have some very cool seminars. We have Karen Burnham doing a lecture series on mill standard 461 and EMC. We have a seminar at the end of the month with Susie Webb on part placement. We have Ken Wyatt in April, and we have a soldering seminar also in April. So if you're interested, and heat management with Kevin Coates. I will send you the link. Okay, so now we can go to the Q&A. Orlan, do you want to take a look at the questions? I think the first one is for you, or maybe for us. Oh, and also we have Steve Carney with us from Sierra Circuits. He's our R&D manager, and Steve is also going to help us answer some of the questions.
Yeah, I see the first question is the actual physical pad size, the minimum hole to pad ratio for class 3 products, designing with the tighter pitch devices is truly a problem where you have the pitch. Again, work with your fabricator on that to see what can be compromised as far as the class 3 products on there.
Okay, Steve, do you have anything to add? The question is from Nathan. I am looking for solutions for DDR designs using VIA in pad on a class 3 design and boards, 62 to 100 thick designs. Class 3 VIA minimum is 24 by 8, which is problematic on small pitch DDR BGA chips. Without compromising class 3 and higher, do you have examples or other solutions?
I would have to see it. I don't have an answer for that off the top of my head. Probably the main thing would be is whether or not it requires an etch back. There are some things we can do with different material sets to get a higher density in those boards, but we'd have to see the design to come up with a solution for it.
Okay, thank you. Next question. For DDR4, how concerned do you need to be about crosstalk between data lines of the same byte?
You need to be very concerned about that, and you need to go ahead and keep those requirements separated. That's why I like to alternate the byte lanes on 2 different layers, keeping all the byte lanes for those particular nets together, but then alternate. So not only do I have that separation that I need, but I got a Z-axis separation also when I'm routing.
Next question. Do we need back drilling for DDR4 and or DDR5?
So back drilling is a cheaper way to manufacture your board to get away from blind and buried vias. Blind and buried vias is a cost driver that drives the price up. So back drilling gets rid of those antennas that you don't want out there. But again, back drilling, you need more space. So now you're sacrificing real estate so that you can back drill and knock those pads out on there. But again, back drilling is very cost, if that's the thing that's driving you in cost. In most class 3 products, cost isn't the factor. The fact that the class 3 product can't fail. So blind and buried vias are normally used, but again, it's about the class of product you're developing, and then back drilling will save you money over blind and buried vias.
Okay, thank you. Can you confirm that there's no maximum length limits as long as they are matched in length? What is the allowable difference between them?
Well, that's kind of a tough one to answer. There are maximum lengths. There are limits to the signal. So the goal is to keep them as short as possible, not looking for max length. And again, your board might not be just within its own environment. You might be taking that signal off the board through a ribbon cable. If that's the case, again, length becomes an issue. So yeah, it all depends on the design, and definitely back to the simulation and simulate that board with the other boards plugged into it for that quality of signal. But short as possible is the goal, whatever you do.
Thank you. Can you speak to using multiple layers on the CAC lines and compensating for different via propagation delays with tight signal to clock? Rely on simulation tools? How accurate are CAD tools?
Well, I'll let Jerry talk about the simulation part of it, but on the multiple layers on there, of course, we don't recommend changing layers. Coming from, we're talking about the DDR, going from the chip to driver to receiver, staying on the same layer, not going through multiple layers, which would add more vias in there, obviously changing the impedance on there because of those vias on there. But again, going back to the, relying on your simulation tool to help you with those. To our tool, as you saw in my constraint manager, is rather accurate, but at the same time, we still run it through simulation for that final golden check that says everything is good on there.
Yeah, and on the simulation side, you have options in extraction. This is where the extraction choice would come in. Because typically what you're trying to get at, if the z-axis type delays are of importance to you, then you probably want to extract using a 3D solver. And in our case, it'll be our Clarity 3D solver extraction tool set. And that will, because what the 3D solver will do is it meshes the conductive areas in all directions, not only the XY plane for each layer, but the vertical directions for the vias as you transition between layers. So the 3D solver will give you a very accurate representation of that. The one I use here is the intermediate solver, the 2.5 dimensionals. That does a full mesh in the X and Y direction, in the plane of the board, but it makes assumptions in the vertical direction. So if you're not really going super fast in terms of signal switching speed, you can usually get away with something like a 2.5 dimensional solver. It's much faster and less hassle to set up, but it's still pretty accurate in the z-axis direction, provided you're not exceeding like 5 to 8 gigahertz in signal switching speed. Once you start doing that, then the vias start making a difference, and so the prop delay needs to be accounted for in that case.
Thank you. Do we have any more questions? Okay, doesn't look like it. Well, thank you very much, everyone, for joining. Thank you so much to the EMA team for doing this webinar with us. Thank you, Vandana, for presenting. Thank you, everyone, for answering the questions. And slides and recording this afternoon. Okay, have a good day, everyone. Bye-bye.